Hello, I'm Robert Stoner, the Deputy Director of Mighty for Science and Technology. Welcome to the third and fourth portions of our five-part webinar series discussing our recently released Future of Energy Storage study. I'll remind you that the study is concerned with energy storage within the electricity system. We weren't directly concerned with traction batteries for EVs, for example. What motivated us to write the study rather was curiosity about the role storage will play over the next several decades in a grid increasingly powered by sources of variable renewable energy, which we refer to throughout the study and will today as VREs, mostly solar and wind. In the two previous sessions, we heard from several study contributors about electrochemical storage technologies and some of the material supply constraints that may determine how widely they're ultimately adopted in the electric power system. We learned that the incumbent technology, lithium-ion, meets the present needs of the grid pretty well, but those needs are very modest relative to what they'll be in the future as VRE deployment expands. And we learned from Elsa Olivetti and Bob Jaffe that the supply of key ingredients, including lithium, as well as cobalt and nickel, will have a very hard time keeping up as demand for grid storage and EVs grows over time. We need other technologies that have lower intrinsic cost and, crucially, can be economic in long-duration applications, like seasonal storage. Getming Chang and Fik Rushet discussed some promising alternative electrochemical technologies, including metal air batteries, that may be helpful. In our first hour today, we'll describe our findings relating to non-electrochemical storage, that is mechanical storage, thermal storage, and low and zero carbon fuel-based, or rather zero carbon fuel-based storage, and specifically the role of hydrogen. In our second hour, we'll focus on our modeling work that examines the evolution of high VRE grids with storage in different parts of the world, and the resulting implications for the cost of electricity and CO2 emissions. It's a lot to cover, and we're going to move quickly so that we can leave plenty of room for questions, as we did yesterday. Please enter your questions in the Q&A box, and we'll try to get to as many as we can in the second half of each of the two blocks. So without further delay, let me introduce the speakers for our first hour on non-electrochemical storage. Howard Grunsbeck, the former Deputy Administrator of the U.S. Energy Information Administration. Robert Jaffe, Emeritus Professor of Physics, and among many other things, the co-author of The Physics of Energy, a wonderfully accessible textbook that I recommend and keep by my bedside. Seiji Engelkemeier, a PhD student in civil and environmental engineering, and Emre Gencer, coming to us from Turkey. Emre's a senior leader of Mighty's Systems Modeling Group. So Howard, let me turn to you and start with pumped storage.
Okay, so pumped hydro storage, mature, widely deployed, long-duration storage technology. A lot of it has been built. The US and Europe and Japan built a lot of it over 1960 to 2000. Ironically, now we talk about long-duration storage as something to complement VRE, but then it was built to complement coal and nuclear for the most part. It still accounts for over 99% of the energy capacity of electricity storage and over 90% of the power capacity of the world's total electricity storage. For the US, only over 98 and over 87% of storage capacity. As you can see from the graphic, the pumped hydro grew rapidly, I guess from 1960 through 2000 in Europe, other Asia, mostly Japan, the United States. But since then, almost all the growth has been in China. The share of total electricity storage by PSH is falling more rapidly for power capacity than for energy capacity. That directly reflects the long duration of PSH. Most of them are at least 10 hours worth of capacity to discharge at full power, but some of them are longer. The economic value of PSH and other forms of storage has generally decreased over the last 20 years, as the increasing role of natural gas generation has reduced the gap between day and night generation costs. So the thought is if you're using gas both day and night, why pay to pump up water at night to burn gas then to avoid burning gas in the day when you could just burn the gas in the day and don't have the round trip efficiency loss. But now with VRE playing a larger role, the thought is there'll be more opportunity for long duration storage, and it'll be even more critical than it was in the era of large coal and nuclear plants. And finally, electricity market restructuring in the US and globally has made it much more difficult to finance pumped storage hydro. So this is just a little look at the attributes. We don't have much time. Over on the right-hand side, I'm showing the cost of both power and energy of all the PSH projects built between or commissioned between 1995 and 2020 in different parts of the world. And you can see that the power capacity is relatively expensive, building the spillways and the water tunnels and the turbines. That's very expensive. In many cases, the energy capacity is relatively cheap, mostly $5 a kilowatt hour to $70 a kilowatt hour, but it can be higher in certain circumstances. So the attributes of PSH, it's a 80% roughly round trip efficiency. That's actually high relative to other long duration technologies, so that's a plus. But maybe round trip efficiency matters less for long duration storage than for short duration storage. Has a long service life, that's a plus. Long build time, not so great. Many site specific elements, so that kind of makes it hard to get down the learning curve with PSH, especially if you're not building very much to begin with. The value of or demand for the PSH services is uncertain, and that's a big challenge. And again, in recent history, it's actually been declining a little bit, and even the existing PSH has been utilized less. It's hard to finance. Mentioned that already. Environmental impacts and siting process for open loop, that's PSH that uses natural water bodies, can be a nightmare and very difficult. Closed loop is easier. There are some potential synergies between seawater PSH and desalination. I think Professor Slocum has looked at some of that historically. And finally, one thing we look at in the box is the use of conventional hydro to store variable renewable energy. Basically, the idea here is to avoid the use of stored water in conventional hydro systems when DRE is available to enable increased generation when it's not. So with that, let me end, and I look forward to questions at the end. Thank you.
Okay, thanks, Howard. So let's turn to Bob now to continue with this mechanical storage technology discussion. Bob, you're muted still.
Let me share my screen. Can everyone see my screen? Good. So I'm going to make some brief comments on compressed air energy storage, another form of mechanical energy storage. Let me emphasize some general features of mechanical energy storage, that it has low density compared to thermal and electrochemical energy storage. Therefore, it typically has a large footprint. In the case of compressed air energy storage, much of that footprint is underground. There are significant geographical siting constraints that constrain the generality of this kind of storage. And it doesn't lend itself to modular installations. It's either there or not there. First, let me describe what compressed air energy storage is. These systems take electrical energy incoming, which is used to run compressors that compress atmospheric pressure air to high pressure, generating considerable heat. The heat is then removed from the compressed air and sent to a thermal energy storage system and the now ambient temperature compressed air is sent to typically a large underground cavern where the compressed air energy is stored. There may be one or more stages of compression. The compressed air is stored, the thermal energy is stored, and then in discharge, this process is repeated in the opposite direction. The compressed air is fed into a turbine and heated with the stored thermal energy, and this process may be completed in one or more turbines, generating electrical energy back to the grid. Thermodynamics places some very important constraints on compressed air energy storage. One is that all of the incoming electrical energy, except that's lost to inefficiencies, is actually stored in the thermal energy storage. Compressing an ideal gas does not increase its internal energy. So the compressed air stores essentially none of the incoming electrical energy. On the other hand, the capacity to do work, or exergy, is shared between both the thermal energy and the compressed air, and both play a role in generating the usable work in the discharge of the system. Often adiabatic compressed air energy storage is confused with another system called diabatic compressed air energy storage. These systems use electricity to compress ambient air and discharge the heat of compression into the atmosphere irreversibly, storing only the compressed air. Then, upon the need to discharge that stored electrical energy, the compressed air is heated by combustion of a fuel, typically natural gas, on its way back through the expansion machines, the turbines, producing the outgoing electricity. Diabatic compressed air energy storage has been deployed at 2 plants, one in Germany and one in Alabama. It is not a storage system. A large fraction of the outgoing electricity is generated, in fact, by the combustion of fossil fuels. It's more appropriate to view this as a Brayton gas turbine cycle, which has been enhanced by the use of otherwise discarded electrical energy to provide pre-compression of the air. We do not consider diabatic air storage in our study because we're only interested in true electrical energy storage. It's important to emphasize the importance of thermal energy storage in CAES. Here's a schematic drawing of a CAES system. You'll notice the compressor feeds the heat of storage into a large surface TES, or thermal energy storage system, and the compressed air into an underground cavern. Since all of the incoming electrical energy is stored as thermal energy, the size and scope of the thermal energy storage system is comparable to other thermal energy storage systems. For example, the storage systems that are used in solar thermal energy facilities to store the solar energy that's been transferred to thermal oil or to molten salt. With that, a couple of comments. The technology readiness level of CAES is low. There have been no successful demonstrations at the relevant scale in a realistic environment, despite many attempts and much media coverage over the past 30 years. It requires a thermal energy storage system comparable to dedicated thermal energy storage facilities, as I already mentioned. It requires underground storage in large, of the order of million cubic meter geological formations that can sustain high pressure, yet have high permeability. At the present time, only brine excavated salt caverns and salt domes have been used for this. The possibility of using bedded salt and sedimentary formations has been considered but not implemented. There are a couple of thermodynamic issues that conflict in the desirability of CAES. The first is that multiple stages of compression and expansion are mechanically advantageous to avoid constraints on the machinery, but they're thermodynamically problematic because they produce air stored at lower and lower temperatures. Furthermore, there's a conflict between constant pressure and constant volume storage of the air. Constant volume is easy to devise in a fixed volume underground cavity, but it requires throttling the air down to lower pressure and discharge. Isobaric storage would allow more efficient discharge, but the mechanical civil engineering issues associated with constructing constant pressure air storage have yet to be conquered. So finally, let me make a brief summary of our takeaways. In principle, compressed air energy storage could store air above or below ground. Because of inherent problems with above ground air storage, grid scale deployment of CES depends on the availability of suitable large scale underground air storage systems. Those are geologically limited and they compete economically with storage of hydrogen and natural gas. Experience tells us that regional analyses of potential underground air storage sites is inadequate. It's necessary to do technical and economic feasibility studies at specific locations. And when those have been done at potential locations in the United States, they've generally found that other than underground salt cavities, the locations have turned out not to be suitable. Ultimately, adiabatic CAS with underground air storage does seem viable. And in some regions that do have favorable geological resources, it may play a non-trivial role in the future. However, geological and geographical constraints and the limited cost reduction potential of what are in fact mostly off-the-shelf components seem likely to make CAS less competitive over time compared to other long-duration energy storage technologies which are maturing. One interesting possibility is that liquid air energy storage, liquefying the air during compression and storing it above ground, offers siting flexibility, relatively mature technologies, and should be explored further in future research and development. And with that, I'll turn the screen back to Seiji to talk about thermal energy storage.
Thanks, Alvin. While Seiji sets up, I just comment that we recently funded a liquefied air, compressed air storage study within the Future Energy Systems Center. So we'll be able to report our initial findings on that within the year. Thanks very much. Seiji.
Great. So briefly, what is thermal energy storage? As we've kind of mentioned before, we're looking at energy storage systems that go from electricity in and then output electricity. And with thermal energy storage, you're storing it as heat in between. So what are the key characteristics of thermal energy storage? One is that you can store heat in low-cost materials, and typically these are materials that are widely available. And that's having a low cost of energy is critical for economical long-duration storage systems. But on the other hand, one of the challenges with thermal energy storage is somewhat lower heat to electricity efficiencies, ranging anywhere from 30% up to 60% on the higher end, and the efficiency increases with temperature. So considering that there's a potential for low costs for energy, but the challenge of trying to increase efficiency, reviewing academic literature as well as commercial efforts, we found 3 design strategies that balance those 2 components as well as technology readiness. So the first strategy that I'll talk about is retrofitting steam turbines with thermal energy storage, and that's typically at temperatures below 700 degrees Celsius. The second strategy is higher efficiency car cycles that operate between 600 and 1000 degrees Celsius. And then third are higher temperature systems that operate at 1200 degrees C And that has the potential for lower energy cost and higher discharge efficiency, but it'll take some R&D to get there. So in more detail on this first strategy, in the bounded box on the right is a simple schematic for a coal power plant. So you have a pump, a coal boiler, steam generator, and condenser. And the idea is that you can replace the function of the coal boiler with thermal energy storage system and a heat exchanger. And this shows a two-tank system, and that you charge this thermal energy storage system with grid electricity, and you can run the plant somewhat as is, and then generate electricity. So we did some analysis looking at the age and capacity of steam turbine plants in the United States. And most of the standalone steam turbine plants, those are coal plants for the most part, are fairly old, built, and they're 30 years of age or older, and the average age of retirement for plants are around 50 years. So that doesn't leave much room to retrofit them and still utilize them. On the other hand, there are steam turbine plants as part of combined cycle power plants, and those have been built since around the year 2000 and more recently. So if those can be retrofitted, they have a longer potential lifetime. And then looking outside the US, most of the steam turbine capacity is in China and India, but there is potential in the rest of the world as well. And an interesting aspect in India and China, since most of these plants have been built more recently, they have more modern technology using supercritical and ultra supercritical steam, which enable higher efficiencies than the subcritical plants that are built mostly in the US. And then moving on to the second strategy of higher efficiency power cycles, this is mostly using recuperated closed Brayton cycles. And the working fluid, so the gas that runs in the cycle, can either be argon, nitrogen, or supercritical CO2. These are the most commonly discussed. And at temperatures of 600 to 1,000 degrees Celsius, you can use either sensible or latent heat storage. Latent heat storage implies that there's a phase change material, typically going from a solid to liquid, liquid to solid. And this can be charged, and this thermal energy storage system can be charged using resistive heating. So, or you can use a heat pump using some of the same equipment operated in the reverse Brayton cycle, so it acts as a heat pump. And the third strategy of going to higher temperatures, 1200 degrees Celsius and hotter typically. The main reason to go to these high temperatures is you can increase the heat to electricity efficiency, which is a key metric for long duration energy storage. And because this is a more long-term technology, the design space is fairly open at this point, with at least two axes being the technology used to convert it, and then how you store the heat, whether you're using sensible or latent heat. So just kind of quickly walking through these four examples. On the top left is a concept from NREL using particles like sand or silica to run a combined cycle system. On the top right is a similar that you're using turbo machinery, but instead you're using a phase change silicon, which undergoes its phase transition at 1414 Celsius. And then on the bottom left, instead of using turbo machinery, now you're using thermal photovoltaic panels, which are similar to solar PV panels, but engineered for a different spectrum. And the concept here uses liquid silicon at 2400 Celsius. And then on the right, bottom right, is a concept that also uses thermal photovoltaics, but now is paired with phase change silicon. So there's a variety of concepts out there, all of which still need a certain amount of R&D before they are commercially viable. So the key takeaways for thermal energy storage is it definitely has potential for long duration energy storage through one of these three different design strategies. And all of them can utilize low cost storage materials with the goal being less than $5 per kilowatt hour thermal as a capital cost for energy. And having this lower cost storage material compensates for the somewhat lower efficiencies. And a benefit of thermal energy storage is that the materials under consideration are mostly widely available, so supply chain constraints aren't as much of an issue. And then lastly, the design strategies, they span a range of technology readiness levels. So there's a potential to use low-cost thermal energy storage today, as well as into the future with lower cost, higher performance. And although it wasn't the main focus of the future energy storage study, there's a brief mention in the chapter about how thermal energy storage can be integrated today with thermal processes as another way, although those systems will look different for the ones used for electricity storage. And with that, I'll turn it over to Emery.
Thanks, Seichi. Emery, go ahead.
Thank you, Seiji. So thank you for everyone joining this like deeper dive on each of our chapters. So I'll briefly talk about the hydrogen, actually the chemical energy storage chapter. But in this chapter, we are exclusively focusing on hydrogen due to the fact that hydrogen is likely to pick up other than other chemicals. And also when used or produced, it's relatively easy to not emit any CO2. So that's the reason why we didn't really look into methanol and other potential chemicals into this chapter. So why chemical energy storage and why particularly hydrogen? So first of all, like the entire supply chain of hydrogen is commercially developed. So we have the production, storage, transport, all of these are really in place. It might be expensive today, but we know these technologies. Currently, we can produce, transport, and sold to the industry as a feedstock, but we don't have a significant consumer market. And here you see basically two types of one like fuel cell and also a type of electrolyzer, PEM electrolyzers for production of hydrogen from electricity. And when we look at the capital costs, which is really the focus of using hydrogen in the context of energy storage, you see there are a lot of studies. And in our chapter, we have tried to synthesize all the available literature during the period of study to look into how the cost will change over time. And as you can see, there are two main options for electrolyzers, PEM and alkaline electrolyzers. And for both technologies, we expect to see a massive cost decline over time up to 2050. But unfortunately, today's costs are quite high. And the reason we are exclusively looking into electricity-based hydrogen production is because this is a future of energy storage study. And for making this a storage option, you need to start from electricity and you need to convert it to another form and then convert back to electricity. So that's the reason why we are looking into electrolyzer technologies in our cost estimates. When we look into how much it costs to really produce hydrogen from electrolyzers, so we have done multiple sensitivity analysis on two key components. One is capacity factor, and in both graphs you see these in x-axis, and the second one is cost of electricity. So ultimately, what we are really trying to do here is store electricity, ideally when it's cheaper, and then convert it back to electricity when we need for balancing the system and for other applications. And the reason we have looked into the capacity factor is because electrolyzers are capital intensive devices, and if you are not operating them at high capacity factors, and as you can see here, the cost of produced hydrogen can be quite dramatically high. And here you can see basically up to 30-35% capacity factor. There's a huge cost of producing hydrogen, and these numbers are shown in dollars per kilogram of hydrogen produced. And after $30-35% capacity factor, we see a decline, a significant decline in cost of hydrogen, and then it is kind of plateaued over the course of all the way to 100%. And this is especially important because for renewable power, we know they are intermittently available, and it is most probably that the capacity factors will be lower than 50% if we are exclusively relying on solar and wind. And so this is another look of the same story, share of total cost for different options, different capacity factors. And this shows very nicely how actually the cost share changes over the different capacity factors. So when we have very low capacity factor, as you can see, most of the cost is on annual capital expenditure as well as maintenance cost, and electricity contributes relatively low to the total cost. And when we switch to 25% capacity factor, we see that the electricity share is increasing. But when we actually switch to 50 or 100% capacity factors, we see that actually the predominantly cost is coming from electricity. So in these cases, if we have cheap electricity or relatively low cost electricity, then hydrogen production can be quite cost effective. And this is mostly the discussions we are seeing in the literature and in the news. Actually, you can really use free electricity to produce cheap hydrogen, but we really need to understand that it is only reflected to the cost of hydrogen if we have higher capacity factors. Otherwise, CapEx dominates the hydrogen cost. And similarly, we want to look into cost of hydrogen produced in 2050, and we have similar decline curve, and we expect these PEM and alkaline electrolyzers will be more cost effective as we move to 2050. This is due to technology improvement, and also building more and more of these devices will definitely reduce the cost. And ultimately, we need to really close the loop and look at the cost of electricity. And for cost of electricity, we really need to understand two factors here. One is, of course, the hydrogen cost. And the second one is how we are using this electricity with different devices. And in this study, we are looking at gas turbine units, combined cycle hydrogen power plants, as well as fuel cells. And this is reflecting the cost of hydrogen to the cost of power produced, and you can see basically depending on your cost marks, we really need to get down the cost below $2 per kilogram to have an effective cost of power produced from these options. And you will see in the next slides as well, we can really produce low carbon and low cost hydrogen, but ultimately, if the power production is expensive, it's less likely that hydrogen will be used for energy storage applications, especially as the only application for hydrogen. So to address that issue, actually, we have also in another chapter, and Katie Wang will share this in the next hour of the webinar. Basically, we have looked at multi-use of hydrogen, and this is what makes hydrogen really unique. So hydrogen is not only an energy storage medium, but it can be used for fuels, for other applications, for industry. And once we have hydrogen flow in the system, then the story completely changes, and some hydrogen can be used for hydrogen for electricity storage, long duration or other durations energy storage. And these will be discussed in much more detail in the next hour. And a couple of takeaways from this chapter and the work on hydrogen. So first of all, hydrogen is a readily available technology. So all the technologies are proven and they are commercially available. The only relatively missing piece is the power production. And this is not because we don't know how to do it, but it is currently quite expensive. But this is, again, not really a technology challenge. Even though low cost of hydrogen, especially on storing, can make hydrogen an effective long duration energy storage medium, unfortunately, the other options, and as you've seen in the thermal energy chapter or pump hydro that Howard shared, there are more effective solutions for long duration applications for now. However, as I mentioned, hydrogen has multiple uses. So this is basically another energy vector like power, and it can be used in the overall economy in multiple applications. And once we have this in the place, then we can really see hydrogen used for energy storage applications as well. And just to re-emphasize, long duration energy storage or any other energy storage will not be the initial point of entry for hydrogen in our energy system. But definitely, once there is a hydrogen flow, it will follow the lead of other applications. And these are the conclusions from our chapter, and I'll stop here and turn back to Rob.
Well, thanks very much, Emre. Thanks everyone. For really interesting talks, and you could tell because the Q&A was very, very active with a lot of questions coming in. And I guess perhaps just to get going, I'll come back to Howard, who talked first with respect to pumped storage. And I guess to synthesize the question, the questions, the big question is, why can't we do this? Why is it that it's economic to build these very large pumped storage systems in China? And the study concludes that it's economically infeasible. There seem to be lots of sites. Someone pointed out an Australian National University study recently that demonstrates that. Can you explain, Howard?
Right. So quickly, we can build them. We have built them in the past. There needs to be, I think, the value of the services provided has to be high. When we had coal and nuclear plants that had excess capacity at night, and we were using oil during the day to generate peak power, that was a tremendous incentive to build lots of hydro, so we could use that low marginal cost power at night and avoid using very high marginal cost power in the day. Right now, with a lot of gas on the system, both day and night in lots of places, the economics, the value of the services is simply not high enough to finance the project. The other thing is the change, and I went over it quickly, from a vertically integrated utility structure where a pumped hydro system could literally be put into the rate base to now we have a much more competitive electricity markets in many parts of this country and throughout the world. And in that world, financing these kind of big projects in many of the same respects as financing large nuclear plants has been difficult. And so it's doable, and maybe with more VRE on the system, again, there'll be a higher value to the services provided by PSH, but PSH also has to compete with other emerging long duration storage technologies. And there really were none in the era that a lot of them were built in the US and Europe and Japan. And, as other speakers have discussed, there may well be some going forward in the future. So it's definitely possible. Projects have been licensed in the US, but they just haven't been able to put the financing together. I think I should stop there.
Yeah, no, I mean, you make a very good point about it. It may be more feasible in non-market parts of the system. Like
certainly China, there's a lot of financing, by the grid operator.
Right, but even in vertically integrated utilities like
right. And in Spain, I believe there's some being built. There's some being built in Australia. It is being built, but let me stop there.
Yeah, so it's almost a peculiarity of the American and European market in these systems that is the limitation there. Emery, there's another question for you. A couple of interesting questions. One relating to recognizing the external costs of hydrogen production come from having to purify water before it's electrolyzed, and also from the release of brines, possible management costs of those brines. Are they included in your estimates of what those costs are?
Yeah, I was just answering to that question, so this is very timely. Thank you, Rob. So it's not included in our study explicitly looking into desalination or other areas that's potentially there is water scarcity. But what we found is basically the water cost, whatever high it is, it's relatively negligible relative to other components like capex of electrolyzers, electricity cost. And also desalination gives also a nice integration opportunity with electrolyzers, so we can also design new systems that will take directly like seawater, as we've been discussing last week, basically, Rob. And also, or we can really integrate these two and use desalination as a flexible load for variable renewable electricity system. So I really don't see this as a challenge, but also it can be another component of making renewables more robust in the context of energy storage.
What about in the positive column, the opportunity to monetize salts that are being extracted? Is that
so
realistic?
like we have not studied in detail, but basically, so like my answer is similar to like carbon black from methane pyrolysis. I think there is definitely an opportunity for smaller scales, but when we look into larger scales that's required for energy transition, I don't think we will need that much brine, that much carbon black, so on and so forth. So basically, these are only attractive at smaller scales when we start these. And I can also give another example from basically using free electricity for hydrogen production. The same analogy applies. So these are only opportunities when we have smaller scales of operations. But for this study, as well as for other applications, we are really talking about massive scales where we really need to create our own opportunity and not rely on byproducts.
I guess, Emmy, just staying with you for a moment, you spent your time at our request talking about hydrogen, and didn't cover other potential fuels, and one that's much discussed now is ammonia, especially for marine transportation, for example, but even co-firing applications. What are your thoughts about the viability of ammonia as another pathway?
Yeah, I think that's a great question, because ammonia as a potential solution is a viable option. But in this chapter, the reason we really left out ammonia is because for producing ammonia, you need an additional step. Basically, if hydrogen is not economical, ammonia will not be economical, because you need to further convert hydrogen into ammonia. However, like there was also a question in the Q&A, like from handling perspective, long-term transportation perspective, ammonia can be attractive. And we know that there are also many manufacturers really looking into ammonia fired power plants or ammonia co-fired power plants that can really handle well ammonia. Like I'm not dismissing, but from cost perspective, there are some challenges that needs to be overcome.
And just one final hydrogen question, because this is stuff that I get involved with quite a lot. There are a number of situations in the world right now, not least in Europe, and the European Commission has called for a sort of a space program on hydrogen or green hydrogen as a replacement for natural gas, and a very rapid deployment of a huge amount of green hydrogen. Is it nonsense? I mean, India has a big green hydrogen ambition. Are these things, just looking at your graphs, I mean, are these things really sort of economically infeasible in the present?
Yeah, I will bluntly answer your question. I think it's nonsense. And the reason is basically for the production of green hydrogen, you need massive deployment of renewable power. And we are mostly overseeing this because like we really don't have that much renewable power, solar and wind. And the deployment of additional dedicated renewable power will take time. And also we will still have the intermittency challenges. So like of course, we really need to push forward. So we need to produce as much green hydrogen as possible, as soon as possible. But again, coming back to the scale issues, it will take time. And also we really need to, don't miss the opportunity to use renewable power for easy to electrify sectors first. So in the case of there is a competition between using green electrons for hydrogen production versus directly using for any other decarbonization applications, I think we should start with the direct electrification pathway and then switch to green hydrogen production. For the one single reason, you can produce hydrogen in other using other options as well, other alternatives as well. And with right methods like high rates of carbon capture, you can really achieve low carbon hydrogen with other pathways. So just due to that fact, I would really prioritize use of renewable electrons for direct electrification applications.
Okay. And Bob, not to leave compressed air storage off the table, although it wasn't that encouraging a story. There's one question that's just popped up, which asks, is there any potential benefit from direct coupling, say, of windmills to compressors that makes compressed air storage more attractive economically? Or are we simply limited by the thermodynamics of the situation and the size of the machines? You're muted, by the way. You're muted, Bob. You are mute, Bob. You're muted. Yeah.
Sorry. There's the siting problem. The windmills would have to be sited near these geographically constrained compressed air energy storage sites. So you'd have to have a lucky coincidence of good wind power and storage, but also conversion of the wind power to electricity is very high efficiency. So converting it to electricity and sending it to a storage site is probably a simpler solution than trying to put the windmill at the compressed air storage site itself.
So you give up a lot of value for a very small gain by doing that. Bob, since you're a physicist, I'm going to ask you the gravity question that also has come up. We've all seen these pictures, some of them in the popular press, with giant machines moving around blocks of concrete, making big piles. There are other examples of trains being pushed uphill and then brought back down the hill when the air conditioners come on in California. What's the problem with that? It seems like such a great idea. Did the study look at it?
I think I'd like to make a general comment, which is raising matter in a gravitational field is what pumped hydro does. It raises water through a head of hundreds of meters and then regains the energy at high efficiency by running the water back through a turbine. Raising concrete blocks or rocks in a gravitational field has the advantage that the density of the rocks is about a factor of 2 or perhaps 3 higher than water. It has the disadvantage that you need an entire engineered system of cranes and railroad trains and other devices in order to raise this matter up in a gravitational field. So by and large, the added cost of all that machinery does not counteract the disadvantage of the fact that you're only gaining a factor of 2 or 2.5 in the relative density of the material relative to water. Mm-hmm. There are some places and some circumstances like the California deserts where there's a lot of unused machinery where this might play a niche role. But as far as a large scale energy storage system, you would have to have them set out on the landscape over the same scale as pumped hydro. And that amount of machinery seems outlandish.
Mm-hmm. Mm-hmm. Okay. Seiji, there are lots of questions about what you were saying as well about thermal storage, and implicit in what you were saying was that there's a big opportunity to retrofit plants, maybe different kinds of plants depending on where you are in the world and what the installed base looks like. But so in other words, repurposing power plants as thermal batteries, charging them up when power is cheap and bringing power back to the grid at times of high demand. Have you looked at the size of that opportunity in different markets? In other words, how many plants are there that really are amenable to those sorts of retrofits? And does this look like it might play a significant role in providing storage capacity?
Yeah, so the analysis that we did for the study was a very high level analysis, just looking at the age and the capacity of the plants. You definitely need further study, like engineering studies on a more plant by plant basis, looking at what the remaining lifetime on the major components are and which components are replaceable and then still economical. So if you run a plant and most of the plant still looks pretty good, but you have to replace the turbine, how does that cost impact the overall system cost? One sort of simplifying assumption, or one possible assumption you could make is that a lot of these plants at the end of their lifetime burning fuels, you'd have to decommission them. So it might be, you could acquire these plants at relatively low cost to reuse them for storage. And that's what makes this retrofit idea attractive. But it would definitely depend on a plant by plant basis, whether it is amenable to retrofitting.
Okay. There were a couple of questions about nuclear as well, one of which maybe is relevant for you, Seiji, another one for Emory. We have a big nuclear plant installed capacity anyway in this country. We're not adding them very fast, but we may in the future with small modular reactors. Does that create, Seiji, another market for thermal storage that could be important?
Possibly, yes. There's definitely people within MIT and in the nuclear community looking at integrating thermal storage with nuclear power plants. The idea being, instead of taking the electricity that you've generated from the nuclear plant, you take the heat from your nuclear reactor, store it temporarily as heat, and then produce electricity later. I think it'll depend a lot on how the reactor's operated, and yeah, I'll leave it there since I'm not necessarily a nuclear expert, but there is definitely a possibility to integrate.
And Emory, the other nuclear question, of course, relates to the production of hydrogen. And I guess the question is that a more economic route to hydrogen than conventional low temperature PEM sort of production?
So basically, like, I think we shouldn't really, we should consider using nuclear for hydrogen production as well. And this can be in multiple ways. Using nuclear power for hydrogen production as a low carbon electricity generator, or other novel methods to use and integrate with the potential thermal part of the nuclear reactor. All of these options can really reduce the cost of hydrogen produced and give us the low carbon hydrogen that we need. So I think like more discussion is needed on the use of nuclear in hydrogen production.
Okay. Let's see where to go next. There are specific questions, Seiji, for you about very low cost thermal storage media, sand and gravel, for example, or crushed rock. Can you talk a little bit about the thinking there and what the study has to say about those and their utility as large capacity, low cost storage media?
Mm-hmm. Definitely the appeal of using these very widely available when you're talking crushed rock is that it's almost quite literally dirt cheap. The challenge is to what temperature can you take it and how maybe pure is the material that you're using. If you're just digging it out, you'll have lots of impurities. As you increase temperature, you might be off-gassing certain things. So you'll want to have some kind of purification process, which will add some cost. And the question is exactly what material are you starting with and how high of a temperature are you trying to go to? And that will impact the overall design. But there's definitely, I think, some serious research efforts in using sand, which is mostly silica, which can go to higher temperatures beyond 600 Celsius.
There's a question for Bob about gravitational storage with concrete. And I guess the question is there any additional benefit in somehow combining mechanical storage technologies with pumped hydro? I'm not sure I understand the question, but it seems to be trying to provide flexibility and at the same time lower the cost. That's a.
I'm not sure I understand the question.
I'm not sure I really fully understand the question either. It looked more interesting when I read it the first time, and it keeps moving around on my screen as I try to read it. But I think the answer is we don't get it. I'm looking for further questions as well. I don't think I'm seeing any that we haven't answered. So I guess I'll throw it open to the panel. I mean, is there a final word from any of you that you'd like to make relating to, I guess, what is the short-term technology that we can use right now besides lithium-ion batteries, or is there one in these non-electrochemical technologies that we've talked about? Are there any valid options out there?
Well, since I didn't advocate for thermal energy, I will say something about it now. I think that if you look at these technologies, the ones which have a high aside from pumped hydro, which is widely deployed, the one which has a high technology readiness level, more or less conventional components, and an opportunity for making use of existing siting conditions with licensing, electrical transmission lines and the like, is the retrofitting of existing superfluous power plants with thermal energy storage. It just, I don't know if Seiji feels that way, but it seems to me that it's really the shovel-ready storage technology that's not been discussed deeply enough.
Seiji, do you want to comment on that? It would have been my answer too.
Sure, it definitely seems attractive, and I know at least the Department of Energy, through some of their programs, has been funding more detailed engineering studies. I don't know about efforts beyond the US, but I think that's definitely one way to go forward. And then another component of that is much of the thermal storage that's been deployed so far with concentrating solar has been using molten salts. But for electricity storage applications, that seems to be too expensive. So there needs to be work on finding and using an alternative material that's lower cost, but still can reach those temperatures.
Okay. Well, thank you to all four of you, Howard, Emre, Bob, Seiji. I guess if there are unanswered questions here, I guess I'd first refer our viewers to the study itself. But by all means, if you have further questions, don't hesitate to get in touch with us. We'd love to hear from you.